All right, let's dive right into this explainer. Today, we're unpacking the absolute foundational building blocks of electricity. We're going to take an incredible journey from a tiny static electric charge all the way to a fully functioning dynamic circuit. It's honestly a fascinating progression, going from basic physical geometry to the complex webs of power that literally run our lives. So here's our agenda for today. 1. Storing electric charge. 2. Current and Ohm's law. 3. Resistance and power. 4. Navigating Kirchhoff's rules. And finally, 5. The RC circuit.
But before we get bogged down in the math and the formulas, it's worth taking a step back to ask ourselves a pretty big question. How do engineers actually harness and control this completely invisible, chaotic force to power the modern world? Well, it all starts with figuring out how to capture it.
Section 1. Storing electric charge.
To capture this force, we have to start with the most fundamental rule of electricity. Opposite charges attract. You've got a positive charge plus Q and a negative charge minus Q. And this creates this invisible electric field between them, flowing straight from the positive side over to the negative.
We can actually harness that specific electric field using a surprisingly simple device called a capacitor. In its absolute most basic form, a capacitor is literally just two parallel conducting plates. They carry equal but opposite charges, and they're separated by a tiny physical distance, which we usually just label as d.
Now, the really crucial takeaway here is that capacitance, which we represent with the letter C, relies completely on physical geometry. It's just a measure of how much charge a device can store for a given potential difference. And this capacity increases linearly with the area of those plates. Think of it like a bookshelf, right? A bigger shelf just holds more stuff. On the flip side, it's inversely proportional to the distance between the plates. Meaning, well, the closer you cram those plates together, the stronger the storage effect. And we measure all this capacity in a unit called farads.
Section 2. Current and Ohm's law.
Okay, so now we know how to store electricity in a capacitor. But what happens when we finally give it a path to move? Simply put, if your capacitor is a storage tank, then electric current is the active flow of that charge escaping through a wire. Current, denoted by the letter I, is just the rate of charge, Q, flowing over a specific unit of time, T. To put that into perspective, 1 ampere of current is exactly 1 coulomb of charge flying past a single point every single second.
If that feels a bit abstract, we can easily visualize it using a classic plumbing analogy. Honestly, it's the absolute best way to make sense of the invisible. Think of a battery, your power source, like a water pump. The pump creates high pressure, just like a battery creates high electrical potential. The water physically flowing through the pipes, that's your electric current. And if you have a narrow constriction in that pipe, it acts exactly like an electrical resistor, naturally slowing the flow right down.
This whole relationship, the push, the flow, and the restriction, is perfectly formalized in Ohm's law. It simply states that the voltage, our driving pressure, is equal to the current multiplied by the resistance, V equals I times R. It's mathematical proof that the flow of current is directly pushed forward by the voltage and then directly slowed down by the resistance of whatever material it's traveling through.
Section 3. Resistance and power.
Let's dig into that resistance a bit more. Going back to our water analogy, a really long, narrow pipe is going to restrict water flow way more than a short, wide one, right? Well, the exact same is true for wires. Electrical resistance increases with the length of the material, and it decreases if you have a larger cross-sectional area. But it's also about what the wire is actually made of, its inherent resistivity, and even its temperature. As materials heat up, the resistance actually changes. And when we forcefully push that current through a resistance, we expend energy. If we multiply the voltage by the current, we get electric power. P equals V times I. This is literally the exact rate at which electrical energy is expended to do actual, useful work in the real world, like lighting up a bulb in your lamp or heating the coils on an electric stove.
Section 4. Navigating Kirchhoff's rules. Now, Ohm's law is absolutely fantastic for a simple loop. One battery, one resistor. But what happens when circuits turn into these complicated webs with multiple batteries and intersecting wires? When things get that messy, we rely on Kirchhoff's rules. These are built on 2 fundamental laws of physics. First, the point rule, which is all about the conservation of charge. It basically says charge cannot magically appear or disappear at a junction. Whatever flows in absolutely must flow out. Second is the loop rule, based on the conservation of energy. It dictates that in any closed loop, the total energy you gain from your batteries has to exactly equal the energy dropped across your resistors.
When you're doing the math for this, the sign conventions are incredibly critical. For the point rule, inward currents flowing into a junction are treated as positive and outward currents are negative, so the whole thing perfectly balances to zero. For the loop rule, as you virtually travel around your chosen loop, batteries and currents going in your direction of travel are counted as positive.
By sticking to a strict four-step process, you can mathematically untangle literally any multi-loop circuit. First, label your currents. Second, identify what you don't know. Third, write out your loop and junction equations. And fourth, solve them. And hey, here's a fantastic pro tip. Do not panic if you finish a page of algebra and end up with a negative current. It doesn't mean you broke the laws of physics. Actually, scratch that. It just means your initial arbitrary guess for which way the current was flowing was backwards.
Section 5. The RC circuit.
Okay, for our final stop, let's combine our primary building blocks. We'll take the resistor from Ohm's law and the capacitor from the start of this explainer and build a highly dynamic system called the RC circuit. Imagine closing the switch on a circuit like this. The battery instantly wants to fill that capacitor with charge, but the resistor is right there in the way, acting like a bottleneck. Because of this resistance, the charge physically cannot transfer instantly. This bottleneck creates a really predictable, measurable delay, which we call the time constant. We represent it with the Greek letter tau, and mathematically, it's beautifully simple. The time constant is literally just the resistance in ohms multiplied by the capacitance in farads.
Because of that time constant, the circuit's behavior over time traces a curve, not a straight line. The voltage across the capacitor slowly builds up in this smooth exponential curve. Meanwhile, the current starts at its absolute maximum and then gradually chokes itself off to zero. Eventually, it stops entirely once the capacitor is completely full and just blocks any more flow.
So, what does this all mean for us? Well, if a single resistor and a capacitor can dictate the precise timing of electrical flow, think about how millions of these microscopic RC circuits are working together right now. By mastering these basic laws of charge, resistance, and time constants, engineers haven't just solved textbook math problems, they have literally built the foundation of all modern electronics, powering the very device you're using to listen to this explainer. Kind of makes you look at a simple wire a bit differently now, doesn't it?